My name is Ruth Marie Clay. I'm a professor here in the physics department. I work on how planetary systems form and evolve, and my job is to introduce our next speaker, Sean Raymond, who is on an extended visit here from the Observatory of Bordeaux in France. Sean got his undergraduate degree from Bowdoin and his PhD from the University of Washington. He spent time as a postdoc at the University of Colorado before moving to Bordeaux. And what he works on is primarily the dynamics of planetary systems and the small bodies that form them. And Sean actually has an asteroid named after him, which is fun. So Sean is most known for really taking the idea that we got this morning that there's chaos in the dynamical histories of planetary systems, and following through and asking the question, how does the difference in the dynamical history of a planetary system determine the difference in the composition of the planets in that system? So you all know that the planets in the solar system have, in particular the terrestrial planets, we call Mercury, Venus, Earth, and Mars all terrestrial-like planets. They're small rock balls. They're all very different. They look different. They have different atmospheres. And we'd like to know, if we look at other systems, how are those differences going to translate? How will things be similar to the solar system, and how will they be different? And Sean has worked on this sort of question. In particular, what makes worlds with water? How do you know, if we look at other systems, whether we're going to find the water that really supports life on Earth? So, Sean?
Thanks. Well, hi, everyone. It's a pleasure to be here. I want to thank the organizers for inviting me to talk to you guys. And so I'm located in France, but as you'll notice from my talking, I'm not French. Nonetheless, I live in France, but it's a pleasure to be here in Santa Barbara. It's really nice to be here. Before I get going, I'll shamelessly plug my blog called Planet. I write about random things related to planets, and feel free to check it out if you're interested. All right, now to the business at hand, water. The purpose of this talk will be to kind of try to explain how planets might get their water. And we're going to play God a little bit and really go into where we think planetary systems form, how they form, and what determines whether a planet like Earth, or a planet that might have the right temperature for life, whether that planet will have water on it or not. So to start off, of course, we live on a planet with water. You can tell that from the ice on these mountains. When you look up in the sky, everyone imagines, maybe some of these little dots have planets around them. And thanks to Kepler and other planet-finding missions that you'll hear about this afternoon, we know now that a lot of those little dots do have planets. They have planetary systems. Most stars probably have planets. Right. This is good news. Right? And we just know this, in the last few years. Now, what I want to do is like I was saying, to kind of play God, let's think about how planetary systems form. And from that point of view, try to determine what factors are important in terms of building a planet like Earth that might have water on its surface, which we think is a key requirement for life. So to start off, what we're going to do is take a look at where in our own galaxy planets and stars are forming right now. So here is an image of a patch of the sky. This is in the southern sky. It's basically towards the Sagittarius constellation. It's the center of the Milky Way. And so when we say the center of the Milky Way, we're talking about the disk of stars. Our galaxy is basically a giant disk of stars, and these clouds come from the cumulative light from a zillion stars that you see because we're looking right through the disk. And here we labeled a few important things in this image. And you can tell this image is dated from the late 90s because Comet Hale-Bopp was hanging around. But I grabbed this from someone who made this really nice animation. So we're going to zoom in on where stars are forming right now. So we're going to zoom in on the Eagle Nebula. And when we take a little zoom in, this is a Hubble Space Telescope image of this nebula. Let's keep zooming in, because what we're seeing here is a giant cloud of molecular gas. And little clumps of that gas are in the process of collapsing. And when they can get dense enough, they form stars. And in the disks around those young stars is where we think planets form. So let's keep zooming in, because we can't see too much yet. Let's zoom in on this little blip here. Boom. This is the famous Pillars of Creation image taken by the Hubble Space Telescope. You guys have probably seen this. This is a pretty famous one. Hubble actually just took a newer version of this same patch of the sky, and it was just released in the last few weeks. It's nice. It's a pretty spectacular image. But this is still a much larger scale than planet formation. So let's keep zooming in. I'm going to zoom in on this blob here. And you can see there's all sorts of substructure within these pillars. There's all sorts of stuff going on. There's things being evaporated, lots of action. And now we'll even zoom in on this tiny little blip up here. And even though there's only a few pixels here, we can see a little clump of gas. And that little clump, we think, is in the process of collapsing to form its own star and its own disk and maybe its own planets. And for scale, that's how big our solar system is right there. All right? So we zoomed way in, and we're talking about a tiny little blip. And this also illustrates why it's hard to find planets, because planets are, they're inside.
Solar system, do you mean the influence of our sun or all the planets?
This is...
What do you mean by that?
You're right. So the question was, what does the size of our solar system mean here? And in this case, it means the orbits of the outermost planets. So going out to, I think it's Neptune or Pluto, one of those. So the size scale of 30 or 40 astronomical units. Yeah, if you took into account the gravitational influence of the sun, it would be larger. Yeah. So that's what we're talking about. And we see these actual disks around young stars. So here's a few different examples taken with different instruments, mostly with the Hubble Space Telescope. And what are these images actually showing you? Let me explain. These dark bands that are blocking something going on in the middle, that's dust. What we're seeing is a disk of dust, and we're looking at it edge on. These were carefully selected to be nice-looking ones. And we're seeing them edge on. And they're all black because the dust is so thick, it's blocking the light from the star. And we can still tell there's the star in there because the star is illuminating all this other material nearby. And so we can kind of see the light bouncing off that other stuff. But this is the action. This is where planets are forming, right inside these kind of disks. Yeah, question?
HH30 or WF2, whatever that is that a green jet coming out of the star? What is this?
Yeah, so this is actually a jet coming out of the vertical part of the star as it's forming.
In what wavelength?
These are in the optical, in visible light. But exactly which wavelength the jet is bright in, I don't know. I think it's in visible light, kind of, yeah. So yeah, it's basically visible light, and exactly the properties of the jets, I don't know. I could look that up for you if you like. So this is where we think the action is, and we have pictures like this, but what we're imagining is something more like this. All right, this is not a real image of what's happening. This is what we think is happening. Okay, so here's a young star up there with a disk of gas and dust around it, and this is where we think planets are in the process of forming. And so there's all sorts of ideas in this image. Here we have a proto-planet, a planet that's getting pretty big enough to grab onto some gas and maybe carve a gap in this disk. You can see there's lots of little bitty structure in there, presumably from objects that are bashing into each other and growing larger and larger. And of course, in the end, in these kind of cartoons, you always end up with something that looks perfect, exactly like us. Because, those are the stories we like to tell. And so what we're going to do now is to kind of play God and imagine, if we're thinking about forming planets in here, the processes that are important for forming a planet like Earth. Yeah, question?
Yeah, I'm wondering why,
Oh.
if you have the star that's forming in the center of the solar system, why do you have, it seems like the lighter elements like hydrogen and helium forming in the star, but then you get the heavier elements forming for the planets?
Okay, that's a good question. Greg, I see Greg in the background saying to ask everyone to hold questions for the end, but I'll go ahead and answer it anyway, because it's a good question. But for other questions, go ahead and ask me if there's something that's not clear.
What was the question?
Okay, so the question is, why does it seem like there's all the hydrogen and helium in the star, but the planets are forming out of rocks and stuff like that? And the answer is, Basically, we think planets form in these disks of gas and dust that are in the process of falling on the star. And they're actually how the star is growing in its later phases. And the disks are made of the same stuff as the star. But when you're growing solid planets, the stuff you're able to grow out of is the stuff that can become solid instead of staying as a gas. And so hydrogen and helium are really hard to condense. They basically stay as a gas, whereas rocks can condense out and become something that you can build solids out of, solid planets like the Earth. And so even though the disk of stuff that formed the planets started off as the same composition as the sun, you tend to get rid of most of the gas and retain the rocks. That's the idea. Okay, so moving along, this is a cartoon that I like to show. Obviously, this is even more of a, artist's impression, if you will, than the other ones I was showing. But I know that the topic of this conference is about kind of the possibility of life on other planets. And that's an active field of study called astrobiology. And it's a really interesting kind of question to ask. And there's all sorts of details. If you want to ask the question of what are the requirements for life on a planet, the answer is we really don't even know. We can kind of limit them and say a few that we think are important, but we can't really say we can't give you a checklist of these 20 things your planet has to have life. All right, we're just not there. One thing that we think might be important is to have liquid water on the surface of a planet, like the Earth does. If that's really a requirement, then you have to have the right temperature. If your planet wants to have the right temperature, that means it has to have the right orbital distance. You're too close, you're too hot. Too far, you're too cold. That kind of special orbital distance is what we call the habitable zone. And this is a pretty active area of research, and so this depends on all sorts of properties of your atmosphere and your star and so on. But kind of the cartoon version is that in the solar system, the Earth's in the right spot, and Venus is a little too hot, Mars is a little too cold. In real life, people have shown that this is not that simple, and it's possible to have a planet that might have liquid water in each of those places. So just to explain, this is just the cartoon version, not the real detailed version. But an important thing to realize is this zone says if you're in this zone and you have the right properties, you can have liquid water on your surface. But there's more to it. You actually have to have water on your planet. You want to have a planet where you get to go and drink your wine. So I used to always choose a local beer, but I drink more wine lately since I moved to Bordeaux. So this is the local wine now. I feel like I'm being converted to the French wave. Anyhow, so you get the idea. You need to not only have the right conditions for water, but you actually need to have water on that planet. You can imagine a completely dry planet that happens to have just the right conditions for liquid water, but it's got no liquid water, so it can't do it. So there's more than one box you need to check, basically. Now, to kind of think about this, we've got to rewind the clock. Think about how planets are actually forming, the conditions under which they're forming. And here's another cartoon version of where we think that's happening. So just in very simple terms, in a disk, there's a slice through a planet-forming disk, a protoplanetary disk. You got the growing star at the center, and then there's a disk of stuff. And it's out of this disk of gas and dust that objects can condense and grow. But what are you growing? Well, if you're close to the star, you can grow out of stuff that condenses at high temperatures. Things like rocks and iron. As you go farther and farther away from the star, you can condense things that are more and more what's called volatile. Things that require very low temperature to be solid. And a very important one of these, for what we're talking about, of course, is water. And so past some distance, and it's definitely not such a beautiful line. It may vary in space and in time. But this is kind of the conceptual picture. Past some distance, the temperature gets cold enough that you can build planets out of water, out of ice. And we don't know where this is exactly, even in the solar system. We think this was probably located at, 2, 3, 4, 5 astronomical units. Does everyone know what I'm talking about with astronomical units? Yeah? Okay. Earth-Sun distance. Just checking. There's a really interesting, when you're trying to think of a planet like Earth, there's a really interesting sort of paradox that comes in. So on the surface of the Earth, Water is liquid when the temperature is greater than 0 degrees Celsius. In the very low pressure environment of a protoplanetary disk, water can't be liquid. It can only be vapor or solid. And the transition from vapor to solid happens at about minus 120 degrees Celsius. Okay, so if you want to form a planet that has, like Earth, I think on the next one, yeah. So Earth is somewhere in here. If you want to form a planet like Earth to have liquid water on its surface, it's got to be hotter than 0. But to have water built into it as it's forming, it's got to be colder than minus 120, right, 150 Kelvin. It's about minus 120 Celsius. So if you want to be at the right place and have the right composition, it's two different criteria that are quite different, actually. So you want to have your planet in the right spot, but you want to have it build it out of some of this stuff here. It's a tricky thing. It's not as obvious as you might think. Now, as you're building your planet, there's different ways of doing this. So you can imagine if a planet really does form just from the stuff that's right here, in basically what we call that is its feeding zone. So the feeding zone, you can imagine, is kind of the radial distance where all the constituents of a planet come from. Right? If Earth really came from material that was all in here, this curve is trying to show where Earth's building blocks might have come from. If they all came from right nearby, then Earth should be completely dry. Right? If Earth's feeding zone was wide, if basically Earth sampled a really broad initial distribution of stuff, then there's a tail of stuff that would extend past what we call the snow line. I don't know if I mentioned this. This is usually called the snow line. In this picture, it's called the frost line. And I don't like that term as much, but they made a nicer diagram with that term. So that's why you're seeing it. Anyway, so the idea is if you have a broad feeding zone, then there's a tail of material that extends out past this zone, past this snow line. And so some fraction of what ended up inside the Earth didn't start here, where it's all rocky and no ice. It started out here. So how the planet formed is important for this. And there's an even more extreme case that we think might happen sometimes. Some planets might form out here and then for some reason move inward. And in that case, you could have a very, very water-rich planet. Because out here, I didn't tell you any numbers, but we think there's as much or more ice than rock to build the planets out of. So you can imagine forming a planet that has a lot of water on it if it formed out here. So now, what we want to do is kind of imagine, from what we know about other planets around other stars, what's the chances of forming a planet like Earth? A planet that satisfies, the requirements that they're in the right place and they have the right kind of composition. Oh no, I went backwards and I have to show you these things again. Okay. So this is a little bit backwards because there are a couple talks coming up that are going to go into the details of how we know what we know about extrasolar planets. So I'm going to kind of cherry pick a couple things that are interesting for this particular story. But the whole story of how planets are detected is coming up, I think, this afternoon. But anyhow, this is an important diagram for what I'm going to talk about. So this is kind of a distribution of the planets that we know right now. On the y-axis is the planet mass in units of Jupiters. And on the x-axis is the orbital distance in astronomical units. So I put Earth on this plot and Jupiter. And I don't want to go into too many of the details here. For the purposes of what we're talking about, let's lump these planets into different categories. So the biggest clump are these planets that are sometimes referred to as hot super-Earths. And that term, a lot of people have argued that this is not a great term to really explain what these planets are all about. But it's already out there, so I can't stop it. And I kind of like it, so we're going to use it. Okay, so hot super-Earths are these guys. All right, that's a big clump. That makes up a lot of planets. There's this smattering of this little clump of guys called the hot Jupiters. They're not very common. Eric mentioned these briefly. They're big balls of gas. That's why we call them Jupiters, because they're gaseous planets like Jupiter, hot because they're really close to their stars. And the other clump up here near our Jupiter are, what I'll call normal Jupiters, or kind of cases that are similar to our own. So the question I want to ask is, if we just kind of divide everything up into a few different situations, how do we think planets might form in these cases, and how does that affect the water content of planets like Earth? Now, I'm just going to chop things up a little bit here. So here's what we know, just in a very simple picture. We think we know that most stars actually have planets. That's good. Something like 15-ish% of stars like the Sun have Jupiters. So they have gas giant planets that are about the same size as Jupiter. About 10% of those, the last time I did the numbers, have orbits that look like our Jupiters, like our Jupiter. The remaining 90% have weird orbits that Eric also briefly mentioned. They have orbits that don't look like Jupiter in our solar system. And there's two criteria for saying something looks like Jupiter here that I'm using. One of them has to do with the shape of the orbit. This orbit, for example, has a very high eccentricity. That means it's not at all circular. And we think that's indicative of basically its formation story, how it got there. And the other criteria is the planet's size. The orbit's size. So orbits that are kind of similar in size to Jupiter's. So only about 10% of the giant planets have wide orbits that are close to circular. Right? The remaining 90% are these weird ones. And the other stars that don't have gas giant planets like Jupiter, we think that a lot of them, maybe most of them, it's not really clear the exact numbers yet, but many, maybe up to half of all stars have these kind of hot super-Earth systems. And I use just one for illustration here, orbiting the star GJ667c, if you like those tag numbers. And what's interesting about this particular case is that even though the details of this system remain to be really well nailed down, based on at least one analysis, there are several different planets, 3 different planets that might be in the habitable zone of this star. So this is kind of a cool system from that point of view. So now we're going to just chop these up into categories. So we're going to call all these cases like that solar system-like. We're going to call these guys angry gas giants because they have gas giant planets that are doing something different than ours. And then these are hot super-Earth systems. Okay. So we'll go through each of these categories and see how we think planets like Earth might form. All right. So to get started, let's talk about the solar system. Okay. In particular, how did the inner solar system form? The terrestrial planets. And here's what we have to work with. So this is the same picture Eric showed, but zoomed in on the inner part of the solar system. And we have 4 terrestrial planets: Mercury, Venus, Earth, and Mars. We have a big gas giant out there, Jupiter, just 300 times more massive than Earth. And then there's almost nothing in between Mars and Jupiter. This is something that's not commonly appreciated because we all learn about the asteroid belt. The asteroid belt's basically empty, but not completely. There's still about 1,000th of an Earth mass in there, and there's some substructure, but actually we're not even going to worry about this too much today. So this is what we have to work with. This is kind of what models for forming the solar system are trying to reproduce. So how do we go about doing that? Well, first we have to understand a little bit about what order things happen in. And this in itself is a super complicated field. But let me just give you a very simple way to break things up. Okay, we think that gas giants like Jupiter form fast. And why do I say that? It's because they're made out of gas. All right? And gas doesn't stick around for a long time in protoplanetary disks. So this is a plot showing for a bunch of different ages of stars, the fraction of those stars that have disks that we think are the disks that form planets. So very young stars, right when they're born, pretty much all of them have disks. Right? They all start off forming planets. They all start off with some gas, basically. By 10 or 20 million years, none of them have disks anymore. What does that mean? Does that mean they stop forming planets? No, it just means there's no more gas. the disk is gone, and the rocks and things that are still building planets should still be there. Right? And in between, you can see it takes something like, the average disk, the 50% disk lasts something like 2 or 3 million years. So what this graph is telling us is that the gaseous part, the gas within the planet-forming disk, only lasts a few million years. So if you want to form a planet that's made out of gas, it's got to happen early. It has to be done forming within, 5 million years or something like that. So this tells us kind of indirectly, because we're figuring this out by looking at other stars. But if the solar system formed in a disk like this, which we think it did, then Jupiter had to form fast. Jupiter was as big as it is now within a few million years, say 5 million years. All right, and this is important. And what about the Earth? Well, I don't have a nice graph to show this one, but there's... Oh, yeah, question?
Can I just clarify, what's T0?
Ah, good question. So different people define this differently. Typically, the most precise ages we have for the solar system come from meteorites. And so when we're talking about the relative timing of things in the solar system, we usually talk about meteorites. And the oldest solids in the solar system are a particular type of inclusion inside of some meteorites. They're called calcium-aluminum inclusions. And those are the oldest ones. And so that serves as T0 from a meteorite point of view within the solar system. For this plot, there is no T0. Oops. So the T0 for this plot, since it's not looking at the solar system, comes from models for how old we think different stars are.
So that's what I'm asking.
So,
is it ignition of the star or pre-ignition?
this would be from, I think it's from ignition of the star. Yeah, I think. The early phases happen so fast that it's not too important whether it's when the cloud starts to collapse or ignition. But I think it's from ignition. So the second part of this is, so the first part being we think planets like Jupiter form fast. And we think Earth actually took a lot longer than that to form. There's a lot of evidence from analyzing different isotope systems within the Earth that the Earth didn't finish forming for something like 100 million years. So this is kind of weird because Earth is smaller than Jupiter, a lot smaller. And yet we're pretty confident that Jupiter formed first. All right, and this is exactly why that is the case, is an active area of research. And I won't bore you with too many details. There are reasons to think that you're able to concentrate basically large cores of ice and solids and accrete gas on them at Jupiter's distance rather than where Earth is. You can probably do that faster. But the punchline here is that we think Earth formed slower than Jupiter. And what did planets have to grow out of? This is actually, maybe I should skip this. This is a bit complicated. I'm going to come back to this in a sec. Okay. Now I'm going to show you a movie in a sec. And the axes are going to be semi-major axis and eccentricity. So I just want to make sure everyone's on the same page about these. These are the quantities from an ellipse that kind of define an orbit. So an eccentricity of 0 is a circular orbit. And an eccentricity of 1 is basically a parabolic orbit. So we're always going to be living between 0 and 1 here. And the semi-major axis is basically a measure of the size of the orbit. So just to kind of illustrate why we care about this, here's just a whole bunch of different orbits that I drew with different semi-major axes, and they all have an eccentricity of 0. So why do we care about eccentricity anyway? The reason is, as you're growing planets, imagine you try to grow planets here. Each of these is a little rock, and they're orbiting the sun. They can never collide. None of the orbits cross. You can't get anything to bash into anything. Now, what if I just take one of those and give it some eccentricity? Now this guy is crossing a whole bunch of other orbits. So collisions can happen. So that's why we care about eccentricity, because without any, you can never grow bigger. Okay? And where does eccentricity come from? In the context of what I'm going to show you in a sec, it comes from gravitational interactions between planets as they grow. And basically, the more massive a planet, the stronger its gravitational influence, and the larger the eccentricity that it can excite in another orbit. Okay, so let me show you a cartoon. This is an animation, of the growth of a planetary system of, say, let's call it the solar system, even though you'll see it's not quite. So what we've got here is a whole bunch of small bodies that are about the size of the moon or so that are going to collide and grow to form something that looks like the Earth. And I've color-coded each of them by their initial composition. So red things are dry. Blue things are wet. How wet? They have about 5 or 10% water. That's about as wet as asteroids get. And we think maybe those represent the initial conditions for how, the stuff that went into forming the planets. And there's this kind of intermediate zone that's not too important. But on this scale, just so you know, Earth is kind of yellowish green. All right? And since we were talking about the sequence of events, in this movie, Jupiter is already formed. So Jupiter is already formed, and now the movie is going to show us kind of the final assembly by collisions and stuff happening of the terrestrial planets. So here we go. Boom. So Jupiter's gravitational influence is to kind of kick things up around here, and just the self-gravity of all this rocky stuff creates a wave of growth that sweeps outward. And this is going to be our Earth, but you can see it's still completely dry there. So it's still red, and you'll see its color is going to change in a second. And the color changing, see there, it just went from red to orange. It keeps changing. What does that mean? That means that some material that started off out here ended up making its way to Earth and bashing into it and bringing along with it some of its water. And so even though we started with a very strong segregation where everything in here was red and everything out here was blue, at the end we formed planets that look a lot like Earth and Venus that themselves are kind of like greenish blue. And so what this is basically water delivery in action. This is a planet like Earth. This is not exactly Earth, but let's imagine it's Earth. The feeding zone of this guy was not narrow. It was wide enough to extend out here and accrete, have collisions from objects that started off out here. Yeah, question?
Did you input the model parameters such that would happen, or did you input model parameters that were based on a physical system that didn't happen?
Okay, so the question is whether I input model parameters to kind of get the outcome I wanted, or whether it's really... No, that's a good question. It's good to question people who do simulations because we always show you the nicest cases, right? So I've run a zillion of these, well, not a zillion. I've run hundreds of these kinds of simulations, and this process is generic. We've tried varying different parameters of the system to figure out what controls this kind of process. And it turns out it's controlled by a number of different factors that I can tell you about another time. I don't want to go into too many details. But the process itself is basically generic. Yeah. It's very robust. It happens. Yeah. And so this is kind of one model for where we think how we think Earth got its water, from just having a very broad feeding zone that extended out to where there was some water. And of course, the picture is not quite as pretty as what I showed you here. Each of those collisions is actually a whole crazy event in itself. Here are a couple of different examples, 2 different examples of collisions that are not nice and sticky. You can have collisions that are so energetic that they destroy the impactor. You can have ones that spin out a whole bunch of material that produce moons. There's a whole very rich diversity in just the collisions that happen to grow planets like Earth. And it's important just to realize that, even though I'm not going to talk more about it in detail. It's not quite as simple as what I was showing of 2 guys being in the same place at the same time and sticking. It's a much more rich process. And of course, we think that the very final large collision onto the Earth may have been responsible for creating the moon. And the details of exactly what kind of collision are required to produce the moon is a very active area of study. And it's not nailed down yet. There's still a lot of wiggle room in exactly how this might happen. But it's generally agreed that it was probably a big impact that did this. So that's our story for the solar system. I'll mention just in passing that there are other models for how the solar system formed that are a bit more complex, and I'm happy to talk more about those later. But kind of that general picture of Earth having a broad feeding zone, and that's where its water came from, is kind of a nice story that fits. All right, now let's look at some other systems that are really not like our solar system. So let's look at these angry gas giants, as I like to call them. So here's another plot that I'm probably stealing from a later talk. All right, so what this shows is the orbital eccentricity, circular orbits down here, very, very stretched out orbits going up, as a function of orbital distance for all the known planets as of whenever I made this plot. Oh, it's just a while ago now. Anyhow, so for a big sample of the known extrasolar planets. And for scale, Jupiter is down here. Jupiter's orbit is almost a perfect circle. Its eccentricity is about 5%. And it's out here. But most planets, especially gas giant planets, don't have circular orbits. This is weird, right? We actually have trouble explaining why Jupiter's orbit is not perfectly circular. There's a whole bunch of models that have been created just to explain why Jupiter's eccentricity is 5% instead of 0 or 1%. And now there's planets that have eccentricities as high as 0.9 something. There's some really ridiculously eccentric planets out there. And there's also a whole bunch of planets really close in. Because we think, right, maybe we're wrong, but we think that planets like Jupiter form out here. So how do planets that look like Jupiter end up in here and up there? And there's kind of two key processes that have been invoked to explain this. Eric mentioned these a little bit in passing, and I'll just reiterate so you guys see this a couple times. One process that can bring planets from out here inward, it's called orbital migration. And the idea is that giant planets are forming within a big gas disk, right? Like we talked about. But once a planet becomes massive enough, it actually affects the disk. And once a planet becomes a giant planet like Jupiter, it can carve a hole in the disk, a big, ring-shaped hole in the disk. And this seems, why do we care in terms of, what is this going to do? Well, remember, the disk is actually in the process of falling on the star. And when a planet makes a hole in the disk that looks like this, it's linked to the evolution of the disk. It's stuck following the disk. Gas isn't really jumping from here into there. It's pushing on the planet and pushing it inward as the gas goes inward. And so this process is called orbital migration. And what it does is if you form a planet out here, it makes it drift inward. The second process that's important is one that goes upward in this diagram. It's called scattering, planet scattering. And Eric mentioned this a bit too, in terms of cosmic billiards. The idea here is, imagine these planets up here formed in systems with many different planets, and all we're seeing are the survivors. Imagine they formed in systems with, say, in this case, 2 planets on nice circular orbits. But for some reason, those orbits didn't stay stable. The gravitational perturbations between planets caused their orbits to change shape so much that they ended up in the same place at the same time. What happens then is for gas giants like Jupiter, usually they don't actually collide. Their gravity is so strong that when they come close, they give each other giant gravitational kicks. And one of the planets is usually launched into interstellar space. And the planet that survives has a stretched out orbit, an eccentric orbit. So we think that eccentric orbits are basically scars from very violent, dynamical histories on these planets. So these are the 2 processes that are maybe shaping this distribution that we see. And so the question we're going to ask next is, what effect do these processes have on the formation of planets like Earth and on their potential water contents? So let me show you guys a couple of movies of this. These are the same kind of movies that I was showing you before, except things will be slightly different. Okay. So now what's different here, we saw this disk of stuff. The scale is a little bit different. It's a logarithmic scale. What's different here is that we're taking into account that there's gas in the disk, and so this planet is actually going to migrate inward. And we'll see what that does. it kind of moves a little slow at first. But what you see is, as this guy goes inward, it pushes some material inward to it. These are specific, special places called orbital resonances. And I can answer questions about them if you like. It's where the orbital period is an integer ratio of the period of the planet. So 2 to 1 there. And these resonances kind of act as shovels, as snow shovels. And as the planet migrates inward, it uses these shovels to push the small bodies inward, interior to its orbit. And about half the stuff gets pushed inward by these resonances, and about half gets a little too close and gets kicked outward. And so if we want to form a planet out at 1 AU here, where the Earth is, then we want to think about this stuff that got kicked out. What happened to it? So now I'll show you the same kind of movie, but one that runs for a much longer time frame. All right, so get ready. The migration is going to be over pretty quick. So boom, it's done. And now you still are embedded in this disk of gas that's going to disappear in a sec. And what we want to see is how planets around here are forming, if they can still form. And you'll see the system will go nuts in a sec when all the gas goes away. And then there'll be this long phase of collisional accretion where things are bashing together to form planets. And the guy that we're going to be particularly interested in is this guy right here. This guy is our kind of not Earth analog. It's a planet with a similar orbit to Earth, but in a very different kind of system. And what's particularly interesting about this planet, it's a little bit more massive than Earth. That's not too important. But it's really, really blue. It's so blue that it's off the scale of the previous movie. And so why is it so blue? It's so blue because all that stuff that got chucked out of here was basically like a rainbow. It was like every different color. What does that mean? It means that the feeding zone of this guy was so wide that it encompassed basically the whole planetary system. And that means that a lot of stuff that came from out here ended up bashing into this guy and bringing all sorts of water. And so this planet, just for scale, the Earth has something like 1 part in 1,000 of water. Right? If you take the whole Earth, it's mostly rock, and if you chop it up by how much mass there is, only about 1 part in 1,000 is water. On this planet, it's about 10%. So a lot more water. Yeah.
And notice that in this model, Jupiter wound up close to the Sun, but not eccentric at all anymore. And Earth is more eccentric, your new Earth.
Yeah, you're right. So in this case, Jupiter is on a nice circular orbit here, and that's a natural outcome of this migration process.
What's the time scale of migration?
Good question. The time scale, since what happens is the planet is linked to what the disk is doing. And so the planet migrates on the same time scale as the disk falls onto the star. So it depends kind of exactly at what time during the disk's history the giant planet forms. But the time scale is usually, 100,000 years or so, something like that. Yeah, so let me just move on because I only have a couple more minutes to show you guys stuff, and then I'll take questions. So I was going to show you guys these artist impressions and stuff, but I'm going to skip ahead and just show you one more interesting movie before I'm done, which is the effect of planet-planet scattering. So planet scattering, this is a nice image movie made by Eric Ford. Remember, what that process is all about is you add up the gravitational perturbations of a system of giant planets for a long time, it changes their orbits, and eventually they're in the wrong place at the wrong time. One planet gets chucked out. And the remaining, like I was saying, the remaining eccentric orbits basically are scars of this past event. They tell us about what happened in the past. Okay. Now, what we're going to do, which will probably be the last stuff I show you because I'm running out of time, this is the same kind of movie as I was showing you before. It's basically the same conditions that form systems that look a lot like the solar system. We're a little bit zoomed out. There's some extra icy material out here, but it's going to turn out not to play an important role for this story. The main difference is instead of having Jupiter and Saturn, here we got Jupiter and Saturn and another Jupiter. And that's not crazy to think of. We think that probably happens a lot. When you form one gas giant, you probably often form many. So let's see what happens. And you can ignore this. This is for a different talk, that plot up there. So don't worry about that. So here we go. This is the same kind of evolution we saw before. Things are colliding and growing. What we care about most are planets around 1 AU. And at this point, after 30 million years, these objects are already almost as big as the Earth. they're doing the same thing we saw before. You see there's water delivery happening. But wait, the movie's slowing down. What's going on? Why is this happening? Oh, so what happened there? What that was, that's planet-planet scattering. That's a dynamical instability in the orbits of the giant planets. And you can see that had big consequences. We were forming our nice system of Earth-like planets. They all got dumped onto the star. That's no fun. So what we did here, what this movie did, is show a simulation that started off with a system that looked a lot like the solar system, at least like the solar system's giant planets. We transformed it into a system that looks a lot like the giant planets around other stars that we see, with large eccentricities. And in the process, we destroyed all the stuff we had to build planets like Earth. So since I'm out of time, I'm going to stop here. I was going to show you guys, this is kind of the downer point of the talk. I was going to show you guys some more hopeful stuff, but I guess we're going to have to be like Empire Strikes Back. And sorry, there's no more hopeful stuff coming. So I'll stop there.
What's the cause of the planet migration?
Okay, so this part, this migration here? Yeah. Okay. So I was trying to explain this before. It's a very active area of research, and it's a very kind of interesting idea. This was figured out long before planets were actually discovered around other stars. Let me explain what's going on here. So what this image represents is a protoplanetary disk that's mostly gas with some dust. Within that disk, the solids, the rocks and ices, bash into each other and form a large object, something maybe 5 or 10 times more massive than the Earth. When an object gets that big, it can really efficiently gravitationally grab gas directly from the disk. Okay? And by doing that, it can pretty quickly grow from something that looks maybe like Neptune, which is 10 or 20 times as massive as Earth, to Jupiter size, 300 times the mass of the Earth. When that happens, the planet is so massive that it has an effect on the disk in which it's embedded. And what's illustrated in this image is that effect. What this is showing is the planet is right here. The planet's gravity has basically carved out a hole in the disk. So there's gas close to the star. The star is not shown, it's right in the middle. And there's gas further out. But there's no gas kind of right along at the same orbit as the planet.
Is there a gravitational interaction between the star and the planet then? I mean, what's it causing?
So the story continues that's a good question. So once this has happened, this actually makes the planet move and migrate. Why is that? It's because the gas is not just sitting there doing nothing. It's evolving. And we think it's evolving as though it had a viscosity. So if you have a blob of something that's viscous, of honey or whatever, you just stick it on a table, it spreads out. Now you take a blob of something that's viscous and you stick it in orbit around the star, what does it do? Well, it spreads out, but it's also going around at the same time. And what happens in time is most of that blob actually falls onto the star. And a little bit actually goes out, but most of it falls onto the star. So that's what we think these disks are doing. And what happened here is when the giant planet carved this gap in the disk, it basically, it kind of is stuck to what the gas is doing. So it's linked to whatever the disk is doing. If the disk were moving outward, the giant planet's orbit would grow with that. But the disk is generally moving inward. And so the giant planet's orbit is driven inward to become smaller and smaller.
The sticking for the disk is a gravitational interaction.
So I had maybe too simple a question, but why a disk? Why not some big oval or even a sphere?
Well, all right, so why do planets form from disks? Well, basically, if you have a clump of stuff that is collapsing, and you add up the angular momentum of each little piece, if you actually got 0, then you could collapse perfectly. But that never happens. You have some net angular momentum. And that basically creates the collapse creates a disk-like structure. That's the least energy way to collapse. And so we think that's true because the planets in the solar system are lined up in a plane. The planets we see around other stars are often in very thin orbital configurations. So everything is screaming planets form from disks. So that's where we go from. Yeah.
Your one model that had the Earth forming looked like the feeding zone was coming from the asteroid belt area. Mm-hmm. I thought the recent data from that European space probe that took water samples on an asteroid was showing that the signature of the water on the asteroid was not the same signature as on Earth. Can you elaborate?
That's a very good question. So let me just show. I think the movie you're talking about is this one. So I think you're talking about the Rosetta mission that measured the composition of water on a comet. All right. So now comets, these guys are not the same as comets. So in this movie, I'll go ahead and play it again because it's sitting right here. But in this movie, Earth is growing at around here. This is where Earth is, and the water originated somewhere out here. All right? The comets are actually much further out. The chemical signature of this water that we know from a certain type of meteorites that we've spectroscopically matched with the class of asteroids that's sitting out here at about 3 AU. Those have pretty much the exact same chemical composition as Earth's water. And so it's a good story. It fits the story that our water came from around here. It does not fit the story if our water came from comets, which originated way off out here, because, well, there's a couple different reasons. One is the efficiency of actually colliding with the Earth, if you're coming from way back here, is very low. It's hard to get enough comets to bash into the Earth to deliver water. And their chemical compositions are also off. And that measurement really was it was already pretty well established that was the case. And that was another measurement in that direction.
Okay, me again. Following up on the orbital migration, from what you're saying, the viscosity is causing the orbit of the planet that's migrating to slow down, and that since it slows down, then that angular momentum would cause... You're right.
There's effectively a gravitational coupling between the planet and the disk that basically causes the planet to lose orbital angular momentum. Yeah.
Mm-hmm. Okay, so... All right, okay, thank you.
Your model had two watery bodies there, one at about 2 AU, and which brought up the thought to me, so we're talking about roughly, Mars, and so you can have rocky planets forming with a significant amount of water, but they may not keep the water. We don't see the evidence, at least on the surface, of a lot of water for a body that's 2 to 3 AU away.
Yeah, that's a good point. So in the movie I showed you, all the water all the water is conserved, basically. Is that a good picture of what really happens? And there's a lot of study these days in terms of if you bash two big things together, you would imagine that the water might vaporize and go away. And it turns out it's not that efficient. It's not that easy to lose your water. And so when you're actually doing the bashing together, you're probably losing maybe half your water, but not like 99% of it. However, on the on the billions of year evolution of planets, then you can lose a lot of water. And we think that Mars, like you're saying, had a much larger water budget when it formed than it does now. And exactly how much is a matter of debate, maybe 10, maybe 100 times more. And that it lost it through some process. Yeah.
So, I had a question, probably has a simple answer, but as the Jupiter-sized body moved in, it seemed to like snowplow the water towards an inner planet. And I don't quite understand how, because of gravitational attraction, it would push it in and not draw it into itself.
You're right. So in this kind of cartoon picture that I was showing here, this is what you're talking about. So what happens here? Why aren't these guys just bashing into Jupiter? It turns out the reason for that is, well, there's two reasons. One is that these special places that are called, let me pause the movie. I think this will pause it. Oh no, that didn't do it. All right, let me pause this here. So these special locations, these are orbital resonances with Jupiter. These are kind of special places where Jupiter can give objects in those locations kind of a kick that goes the same direction each time they pass around. And in effect, what happens is objects, these two resonances, this is basically anything at this point has an orbit that is half the orbital period of the giant planet. Here, it's one that's 2/3 of the orbital period of the giant planet. And so those spots, they act as like I was saying, it's kind of as shovels and push things interior to them. So in some cases, you can actually have everything in here pushed inward. But some stuff, like you were saying, gets unlucky. It's in the wrong place at the wrong time. It comes close to Jupiter. So why isn't more stuff bashing into it? And the reason is that Jupiter's gravity has a very wide reach. And so you can imagine the probability of something actually bashing into Jupiter is very small, because anytime it comes within a very large distance, Jupiter can give it a strong gravitational kick. But only if it comes really right at the bullseye will it hit the planet. And so Jupiter's gravity is so much stronger than its size in some sense. That's why, there are a few objects that do end up bashing into Jupiter. But it's basically the difference between its gravitational reach and its actual size is the reason for that.
I had a question very similar to the 2 questions ago, but about Venus, just because in one of your pictures you had also a Venus-type watery planet. There is some evidence that there used to be water on Venus, but, could you say a few words about?
That's a good question. Venus is quite a mysterious place, because what we see now, we're not sure if that really represents what it looked like after it formed. And there's some evidence from the surface of Venus that its surface is at least something like 500 million years old. The whole surface looks like it's about the same age. And, it has this very thick atmosphere. And there are some models that invoke that Venus started off more like Earth and then transformed for some reason into what it looks like now, for either geological processes or other ones. And so trying to rewind the clock to what actually happened in early Venus is very tricky. There's lots of people thinking about that. From the point of view of the kind of model that I was showing you, I keep going back and forth between these two movies, but from the point of view of this kind of scenario for formation, we would expect Venus to have a similar formation history to Earth. That being said, during the final phases of formation, you're down to just a few bodies that are bashing into each other. And so in that regime, it's kind of you're tossing a coin as to what your next impact is going to be. So it could be that Venus's impact history, even though it's very close to Earth and it's very similar in size to Earth, that doesn't mean that its impact history was the same. And we just don't know. That could have affected its water content and its current state.
Just a question. I know most stars are binaries. Is that true? Most stars are binaries?
Yeah, they say 3 out of every 2 stars is in a binary system.
Cool. So I wonder, in terms of co-formation, could the planets be forming at the same time that the stars are collapsing, and these large Jupiter-sized planets, when they're that close? We have 1 or 2, 3-day periods for some of these hot Jupiters. How could that happen? It just seems like they...
So binary stars, yeah. This is a super interesting thing. You're right. There are all sorts of different kinds of binaries. There are binaries where the stars are very close to each other, and basically everything between that and stars that are, at 1,000 AU orbits or 10,000 AU orbits. And what we've learned is that there's also a variety of planets that go along. So the Kepler mission has found one of its coolest discoveries that you probably saw in the news were Tatooine planets, were cases where you had, and the guy who did it is right here. It's Bill Welsh right here. So they're basically, these are planets that orbit around very tight binaries. So two stars are on a very short orbit, and then a more distant orbit, you have planets. In some cases, up to 2 planets, I think, or no. Are there any more than 2?
Yeah.
Oh, okay. So, yeah. So that's one situation where you have a tight binary, and there's planets that are orbiting, and they're even orbiting in the same plane as the plane of the stars orbiting each other. Now, they've also found cases where the stars orbit each other in a given plane, and there's a planet that orbits in a different plane. And the plane of that planet, because of the very strong gravitational interactions with the binary, is actually precessing and constantly moving. And so it's not a kind of clockwork thing where you can say, oh, this planet passed in front of that star now, we know exactly when it's going to happen again. It's very complicated to dig the signal of this planet out of the data there. So that's just for close binary stars. Then for every other range of binary star, there are cases where planets have been found. For example, there are cases where the binary is out at very long orbits, and you see planetary systems around one star and everything in between.
If you include the temperature of the planet in these graphs as the evolution proceeds, does it become cool enough for water to condense out on these planets, or does it dissociate?
This is a very important issue. So as you're actually forming a planet with water, what's that water doing? Is it sitting there in a steam atmosphere? Is it having chemical interactions with molten rock that are helping kind of bring it to the interior? During the impacts, are the impacts energetic enough that you actually bury water inside the planet, or does it all stay on the surface? Do you have impacts where they're so energetic that they're blowing off water or the atmosphere from these planets? And these are just questions. Each of those questions are active fields of study. And so people are thinking about this now, but there's no one answer like this is always going to happen. Each of those processes is important in terms of determining the final planet.
Let's thank Sean again, and I think we have some more discussion time coming up, so we'll save our questions for that.
All right, thanks. Thank you.